All right.
So welcome everybody to our last NGTS seminar of this semester. I would like to thank you all who joined these seminars during the semester. We have had like 13 seminars, our 13th and last seminar today. I hope you have enjoyed the seminars and you have learned you have got some ideas for research or stuff that are being done in the transportation area. Without further ado, I would like to introduce our distinguished guest today, Professor Jorge Laval. Professor Laval is a professor at the School of Civil and Environmental Engineering at Georgia Institute of Technology, Georgia Tech. He has received his PhD in 2004 from the University of California, Berkeley, and has received his bachelor's in civil and industrial engineering from the Catholic University of Chile in 1995. His research interests are traffic flow modeling, in general traffic simulation and modeling, and congestion management, and having a better research on a better knowledge of urban congestion. Thank you so much for being here today with us, and the floor is yours.
Thank you, Rafa. Appreciate the nice introduction. I guess we still need the presentation shown here. I'm not sure what to press, to be honest. Okay. So yeah, this should be showing up shortly. It's my great pleasure to be here today, especially because I have good friends here. Yafeng Jing, we go way back. I'm not going to disclose any dates, don't worry. But by the time we were postdocs in Berkeley, we really hit it off there. And then Rafa was just graduated from Georgia Tech in December. And then Yafeng was kind enough to offer a postdoc. So I'm really excited to be here. And most of all, this is my first trip before the pandemic starts. So it's been like 2 years that, and I took my first plane ride. So it was like a whole new experience. So yeah. So today I'm going to talk about a topic that has been brewing for only a couple of years, actually, maybe 1 year, I should say, that really changed the way I think about research now. I should tell you a warning that many of the concepts are not going to be very familiar to you. And that's why I put implications for education a little bit. Because I think what I'm getting at is that we really need to start from the ground up. So teaching some of these concepts in our engineering curricula, all right? So mainly, it's going to be concepts that come from the physics community. And let me quote my advisor, Carlos Daganzo, who's one of the great luminaries in traffic flow. I think he tells us, all his students, always thinks like a physicist, right? But he, without telling you really, or without having you take courses on physics or anything. It's just like a mindset, okay? That took me a while to learn what it is, and I think finally I kind of get the gist of what he meant. So hopefully that will transmit today, okay? So recently we've hit a few research roadblocks. So I'd like to talk a little bit about these in a minute. So I want to talk about signal control very little bit, just because Yafeng is here and I know he likes the topic. Right, so in all these topics, there's some point where it's like you cannot go any further. These problems are all NP complete, right? They're so computationally intensive, and so it's easy to get lost and to get the results that you were expecting. So for example, Rafa worked on the second topic, so MFD estimation. What is the MFD? MFD is going to be like the fundamental diagram for a road, but for the entire city, right? It's like you take the average of the flow and the densities that you observe in each street on the network. And by doing that, you're going to get a nice shape. And the idea is that just knowing that shape of the MFD, you would control the entire city very simply, okay? But to do that, you need to know the shape of that MFD. So that's what Rafi was looking at. So we got data from several countries that are available now and tried to estimate the parameters of those. So we got good results for 5 or 6 cities. And that's, yeah, luckily yesterday or the day before, we knew that the paper was finally accepted in Part B. So if you're interested, that'd be a good read. But there were other cities where the parameter values we obtained were not very, let's say, expected. Like jam densities were super high or super low, or the free flow speed, et cetera, right? So why is that happening? And we really didn't know. Now I may have a clue, and that's kind of the topic here. So the reason behind that is going to be the reason also why signal control might not be as effective as you would think in congested situations. And also something that also affects the way we should design autonomous vehicles, right? So we have projects going on in that direction. And what happens there is that it's very difficult to predict the behavior of the leader, right? In traffic models, maybe you've heard of car following models, such as the main type of models, you follow your leader with a very specific rule, right? So autonomous vehicles is a perfect example of that. But we need to figure out what are the best rules, right? And what the car manufacturers are doing is coming up with these models such that there's no accidents and that the level of comfort is decent, right? But they don't care about congestion. So, and the research shows that if you were to, let's say everybody has a Tesla, and if you were to drive it, congestion would get a lot worse, right? Because they have these string instabilities that will cause these congestion waves to get worse and worse. And so that's not a good picture. So the research is how to make those better, those models. And then we kind of hit the same roadblock. So at some point, you start getting the results that you intuitively would have expected, right? And then what's the reason for that? All right, and now let me talk about, in a bit more detail, about this signalized control. So we have a paper, which you can find in preprints or archive, I forget where we put it. All right, where we show what's in the title, right, is that if you try to control a signalized urban network, now this has to be a big network, okay, super big network. Really, traffic control has its limits. Okay, so what I'm showing here are different MFDs. So we have density versus flow on the whole network, right? You can think of the average. And then we have 3 kind of policies. The green, you can think of a good policy, maybe you're familiar with max pressure algorithm, something like that, right? And then the random policy, which is what it sounds like. So you just give random greens and red, just like that. And the red one is the worst possible policy. So you're given the green to the smallest Q, right? Which doesn't make any sense. But we wanted to have like we wanted to bound. So, right, all the controls will give results that should be in between the green and the red, right? That's kind of your space of MFDs as a result of these policies. All right? So the first surprise is that the worst possible policy is actually not bad in severe congestion, right? So when you're up here, and actually they all give you the same outflow or throughput in the network, right? So, and it's kind of intuitive, right? When you have a lot of congestion, no matter what you do, you're going to have the same output. right? And that's a property of the network more than the traffic control, right? Although some people might say if we get rid of signals, right, and have these connected vehicles do these, let's say, novel type of crossing the street, crossing the box of the intersection, maybe we could get more flow up here. I highly doubt it. I highly doubt it. But yeah, I guess we will see. All right, so I think this region over here, it's kind of part of the physics of the network. I mean, you cannot change that. That's a conjecture. All right, and then in free flow, which would be this part, right, where the density is very low, you see some difference, but you see also a big overlap between the random strategy and the best possible strategy, right? So in those two extremes, really doesn't matter what control policy you use, right? You always get kind of the same outflows. Now, the trick is up here. It's in the middle, right? And we're going to call that today the critical state. This is a capacity state, right? And yeah, often we think of the middle density here as the critical density, right? Yeah, so that's kind of an observation that we made in this paper. Now, the implications when you apply deep reinforcement learning, for example, is very, very striking. So in deep reinforcement learning, right, you're trying to calibrate the parameters of this neural net that will control your traffic lights, right? And then you get input from the simulation environment, and you learn as you go, so to speak, right? So in a first step, you have to train the network. So you have to figure out what are the parameters of that neural net that are kind of optimal, okay? So what we found is that, so this density here in each one of these panels is the density that you use for training the neural net, okay? So what we find is when you train with the density in free flow, right, so up to around here, you get great results. Now, why do I say that they're good? So the blue dash curve represents kind of represented actually the green curve right here. So it's kind of what you would expect a good policy to do, right? So if you train the net with small densities, again, in free flow, you get good results. But as the density for training increases, all right, you see that the resulting policy, which is in gray here, deteriorates more and more. So this was we thought it was a very interesting result. But unfortunately, we have faced a lot of pushback from the reviewers, I guess it's in this case. Right, so they don't like the idea that DRL is not as effective as we hoped it would be. We've tried many DRL methods, right? Some of you may know that there's a vast collection of alternatives. But what happens is that this is a network property. It's not a property of the DRL algorithm. So it's something about congestion that is driving these systems a little crazy, to be honest, okay? So one of the things that to deal with this would be to only consider data that is in free flow conditions to train your neural net, right? And then if you have congestion, then you discard the data. Don't use it for training because it's going to get worse and worse, right? Now, that concept is also not very intuitive because people in this big data era, right, we think that the more data we have, the better. And we think that we can do anything if we have enough data, okay? But unfortunately, what we're finding is that urban networks are not like that, okay? We're saying only consider the free flow data. The rest of the data, well, I'm being recorded, so I'm not going to use strong words here, but if you get congested data, just throw it away because It's not going to be beneficial. So again, why is this? Why is this happening to us? And that's kind of, I hope to provide a gist of an answer today. By the way, please stop me at any time, ask questions, comments, okay? Because I know these are, yeah.
I don't know if you plan to talk about this later, but so can you tell us a little bit about the action space and the reward function in your
Yeah.
learning?
So my focus in general is always to use the simplest possible setting, okay? So in this case, the action space is very simple. It's either, so you set a time, like a minimum green time, let's say 10 time steps. And then at every 10 time steps, the decision is whether to extend the same color of the light or to change it. And we only have two phases, just to make it super simple. Yeah. And then the reward function is the outflow from the intersection during that cycle.
So you use simulation?
Yeah.
Okay.
Yeah. Right. Yes.
I was wondering, how did you perform these experiments on the left? Because usually when we consider MFDs, we expect that the uncongested part, so on the left side of the critical density and so on, it should be low scattered.
Right.
And fine and easy to control and so on.
Yeah, so
that's where we want to keep things.
That's an excellent question, actually.
And after that, it gets chaotic.
Right.
Full of hysteresis, and there I don't see that effect, like the effects.
Right. So actually, when you look at real data, you're typically only observing up to around here. We've never seen this congested branch. So this is only in simulation. So that's. And the other thing is that in MFDs, you tend to get a lot less scatter than if you look at a single loop detector, right? So if you've seen the MFDs in the literature, the scatter, yeah, you're right. So it's always here, there's very little scatter, and then here you get like more scatter, right? Yeah. Here we did a lot of runs, maybe that's why, so the average kind of tend to converge here to a smaller scatter. But yeah, I guess the answer is by performing millions of runs in that way, yeah. All right, so let me talk about the conjecture then, that why this might be happening. So before that, let me show you why SQF gives you good flows. So you saw a simulation in congestion, right? So let me play it again. And here we're given the green to the smallest Qs, right? So at the end, so you start and the point bounces around a little bit. But then what happens is that the system kind of organizes itself to find this thing, that it's an axis that would get permanent green, right? So that's kind of what it converges to, just by applying the simplest route, okay? And that's why you tend to have the same flows as any other policy, right? So I think we have one more. No. All right, so it's the formation of these axes with permanent green that explain a little bit why you have a good flow here. So what's going on there is that it's like you have a big dam, right, holding water, and then you have maybe one hole, and then you try to fix it, but the water's going to come out the other way. So it's kind of inevitable of networks that they will produce a given amount of flow, which is independent of the traffic control. Anyway, so that's what I was planning to talk, right? At the end, what happens is that the conjecture that we have is that really we have been looking at traffic flow maybe with the wrong eyes, right? Traffic flow is a fractal object at the end. And this is where it comes tricky now, because these concepts are not taught in our curriculums, right? So I'll try to emphasize the main points, really, okay? So I'll talk about cellular automata, power law distributions, and let's see how far we can go, all right? And again, please feel free to stop me at any minute. All right. So I wanted to show this because these are the simplest models for traffic flow, all right? These cellular automata models. Now, the idea here that I want to draw from physics is this concept of universality, okay? And this is a very powerful concept. And what it says in a nutshell is that for a given complex system, when you look at macro variables, they tend to have an order, okay? And the way that order works is the same in very many different systems. You would have the same kind of equations that drive these kind of equilibrium states of these complex systems. So at the end, what happens is that the details do not matter. The details of the system, the detailed rules that you have of how people behave are not important when you're looking at this macroscopic behavior, right? When you take a limit for a very large system and for very large times, for example. Okay, these all tend to the same thing. So what physicists do is they focus on the simplest possible model, simulation model, to try to understand these all other type of systems. Okay, so in our case, it means that the simplest possible traffic flow model will be able to tell you everything you need to know about urban networks. Now, but by everything you need to know, I mean, again, these kind of macro state variables, the tendency to converge to some sort of equilibrium, in a sense. All right, so let me tell you just how CA models work. They're very simple. They're probably the simplest programs out there. All right, so we start with a single set of a line of boxes, right? Empty means gray, and then if you have a car, that would be blue, right? And then you apply these rules, right? So you take 3 at a time because you want to predict the next row, right? So this is t equals 0 and t equals 1, and you evolve the thing, right? So you take the first 3, that would be this case, and this means that the next cell, the middle cell below, so this one right here, should be gray as well, right? And you do that for all things. Let's check this one. So if you take these 3, that would be this case, right? Which means that the cell in the next time step should be blue, like this one, right? And then you're going to do this over and over and over. These are what we call the one-dimensional cellular automata. This particular rule, it's called rule number 30. All right, and maybe some of you know Wolfram is the creator of Mathematica, which I use all the time. He thinks he made the discovery that when you apply this simple rule, right, you can't get any simpler than this, you get complexity, right? You get a pattern. So you start with a single one up there, and then you run this rule, and then you get all this, seemingly random patterns. And it's in effect random. All right, there's been many studies to try to get like a shortcut. Like if you're here, can you predict what's going to happen in 10 more iterations? And the answer is you can't. The only way to predict what's going to happen is to run the simulation, run the rules. That's a very powerful concept. Because, in calculus, we're used to, you just plug in a value of t and the equation will give you the state of the system at t, right? But this is saying no. The computational world doesn't work like that. Even starting with the simplest rules, you get a behavior that it's unpredictable. The only way to predict it is to run it. All right, and that's why all the problems in urban networks are so complex, because there's no shortcuts. There's no shortcuts. All right. Now, let me go very quickly. So these patterns in nature, according to Wolfram, they follow these simple rules. So in a sense, nature follows the simplest possible programs, right? And the reason we see complexity is because of this phenomenon, that even starting with the simplest rule and simplest initial condition, you get this overwhelming complexity that, as humans, we cannot understand. All right, so turns out to be 255 CA models, right? Starting with a single initial point, you see what happens. And this one that seemingly looks very boring is the one for traffic flow. CA rule 184. Okay? So the same concept, right? We're going to start with a single car. So that would be one car, and then the road ahead is clear. So in successive time steps, you're going to have just, the car moving at free flow speed. Okay? Same thing if you start with a fully congested road, except for the last square here. This would be like a hole in traffic moving upstream, right? Like a void. If you took a picture, you would see cars all the way up to here, and here you would see the pavement, and then again cars, right? And that hole kind of will have the same trajectory as a vehicle, right? And this is a duality that we have in traffic flow, is that mathematically, free flow and congestion are the same, right? And this is the best way of showing that, I guess. All right. Another thing I should mention, so this might seem complicated, even to try to understand, but what it comes down to, in the case of traffic, the behavior would be advance one step or one square if you can. So if you can means if there's nobody in the next box in front of you. So that's traffic flow at its minimal. It's move if you can, I guess you could summarize it. Okay? And that's encapsulated in this rule. All right, so if you run it 4 more time steps and with random initial conditions, you start getting patterns. Maybe some of you are familiar. So X would run this way, so space, and time runs downwards, right? So this would be like a stop-and-go wave that's going against traffic. Maybe I can point out a trajectory of a vehicle would be this one, right? So it goes at free flow speed, then has to stop in the stop-and-go way, and then maybe advance and stop again, and then like that. Okay? So you start to see the patterns that we do see in reality. Maybe not exactly the same, of course, but very similar. All right, and then if we run a longer system, that's what you would get in the top left, I guess, for you. Right? And all these figures would be if you consider a stochastic version of that same thing, which means that if you're able to move, there will be a probability for you for not to move, okay? And that probability has the richness of generating all these patterns over here, okay? Yeah, these patterns, hopefully they remind you of something. Anybody would like to share what they resemble to you?
Mountains?
Mountains, very good, yeah. I can see, yeah, like the ridges, and you can interpret these as shadows and this as light, right? Any other thing that comes to mind from nature?
Maybe like a tree bark, not sure.
A tree bark? Yeah. Yeah. Sometimes I see like water ripples, right? okay? And this connection is not coincidental. It turns out that traffic, we can call it the traffic surface, right? Because it looks like a surface, and actually it is a surface, has been studied by physicists for a long time. And recently they have very beautiful results that I hopefully I'll have the time to share with you. All right, but what you see here, these are fractal patterns, right, that we see in nature a lot. So yeah, landscapes are fractals. If you look at the mountains, those are fractals. All right, very quickly, why this simple model is able to kind of be the model for traffic flow. Right, and what I showed here is that the fundamental diagram doesn't really matter, or the shape of the fundamental diagram, right? This is density and flow. Again, all those transformations that you saw are linear transformations of flow and density, and it turns out that you would get the same results regardless of the shape of the diagram you choose. So that's why that simple model is kind of a model for all types of fundamental diagrams. All right, now let me talk about power laws, because power laws and fractals, they go hand in hand, okay? Well, and not only those, we have chaos, right? We have complexity. Those are all kind of synonyms. And then phase transitions I would like to talk about. All right, but what are power laws? So Mandelbrot was one of the first to study fractals seriously, and he noted that the price of cotton, I think it was, it doesn't follow what people thought it should follow, which is a normal distribution, right? This would be a normal noise. So, all right, so this is the S&P 500, the percent change in one day, okay? So obviously you see that's the housing bubble, right? Collapse, that's the COVID market crash, right? And those do not obey the normal distribution at all, right? They don't look anything like that. And if you plot a histogram of these guys, and this would be the normal distribution, you would see there's a very large peak that the normal doesn't capture. But most of all, and more importantly, is the points that you don't see here. So there's points here that they're so infrequent that you can't see it at this scale, right? But here would be these market collapses, right? 10% either gains or decreases, right? So by the 1960s, for Mandelbrot, it was clear that the normal model doesn't work. Unfortunately, to this day, we keep teaching the same things to, well, not me, but we keep teaching the same things to our financial engineers or MBA students, right? Everything based on the normal assumption. So yeah, there's a maybe pessimistic view of what's going to happen in our field. Might take 50 years for these ideas, hopefully less. All right, so when you plot a power law in a log-log, the signature is that you see a straight line, all right? So here we plot the probability that the random variable is greater than a given value x, right? And yeah, you see the data. If it's going to be power law, you're going to see a straight line, all right? And let me just flash that's Google's market. This is the population in different cities for France. So this would be Paris, Marseille. Which one is this?
Yeah.
Very good. Very good, very good. And so on and so forth, right? This is known as Zipf's law for cities. The same law exists for the frequency of words, right? If you plot the word frequency, this would be the word the, right? I think the second one is off, and so on and so forth. They are all power laws. And the slope of this line, which is alpha here, tends always to be around 1, which is very problematic because it turns out that when you have that value, there's no mean or variance for this random variable, right? So that means basically they're unpredictable. They're, right? They don't have a mean or a variance, which is what we learn all the time. So the law of large numbers doesn't work anymore. So you keep getting data and hope that the average converges to something. If you have a power law, it's not going to converge. And that's a really serious problem. All right. GDP for countries, the land area of countries again, the railroad length, road length, etc. All power laws. Okay? So I'm not sure about this figure, but I think 90% of the random variables in civil engineering are power laws. Okay? That's why I think this, the way we are teaching statistics, starting with the undergrads, it's overdue for a change. All right. Why are these power laws so prevalent? Okay? There's many reasons that we still don't have a full understanding. It's really kind of magic at this point. But for the case of today's result, this is one very important. So if you have a random walk, right? So what is a random walk? Imagine you flip a coin. You start here, you flip a coin. If it's head, you move to the right. If it's tails, you move to the left, something like that, right? So your position would change like that, and would describe this random walk process. Okay. Now, these random walks are also known as Brownian motions, right? And they're everywhere in nature. They're everywhere. Okay? And turns out that this variable is a power law. So what is this variable? It's called the return time. So you're at a given level, right? 0 in this case. So the time it takes for the process to reach the same level of 0, is the random variable t, which has a power law with exponent 1/2, which is it's in the area where you don't have mean or variance, right? So everything is trying to predict that is impossible. Basically, is what it means. Prediction is impossible. That's one of the main concepts. All right, and the other result we're going to use in a minute is that the area defined by this return period, right, has this, what we call Airy distribution. Now, this is a very new distribution. This result may not have more than 10 years. But the Airy distribution, Airy processes are appearing everywhere now, everywhere. I mean, every day you would see a new paper in that direction, okay? And in fact, the traffic flow surface that I showed at the beginning, it's an Airy process. And that has huge implications for our understanding of traffic and urban networks. All right. How long do I have, do you think?
20 minutes.
Really? Okay. All right. Yes, please.
The reason that we don't have a mean and variance is because the return time could be to infinity.
Exactly. Yeah. Great. This is a very special. Actually, it took me a while to get to this picture that showed kind of various up and downs like that crossing the axis. But yeah, a typical simulation, you would have this going, to infinity. Really. Yeah. Yeah, that's the right intuition. Yeah. And the other intuition is that once you're at 0, right, you tend to bounce around a lot at the beginning, maybe, right? So these areas or these times are very short. And that's kind of the power law behavior. You have many observations with very small values of x, but then you have these giant like market crashes, but they're very few, thankfully, right? Yeah, so that's power law behavior. All right. Now, why is this appear in traffic? One of the reasons is that we're toying with the conjecture that traffic is really like a fluid. A fluid undergoing a phase transition. So Phase transition is just when you boil water, right? It goes from liquid to solid or to gas, right? The changes in the state of matter. And traffic is a fluid like that. So if the cell has a vehicle, you can consider that as a liquid, right? And in free flow, it's a gas. Congestion is kind of a liquid. That's the idea. All right. I talked about universality already, so it's good. So going back to these power laws, so when you have universality, it turns out that the mathematics or the whole thing is defined in terms of the power of that power law. So that alpha we were talking about. Okay, so an example is the beta. This one turns out to be very relevant to traffic for the following reason. Let me skip these two for a minute. So here you have, these are results from the 1940s, okay? And it shows the reduced temperature. So that's the temperature divided by the critical temperature of many fluids. Yeah, I don't know what these are. I think I know that one. It's O2. All right, and here you have the density, the number density. So is the particle density is like the density in traffic, actually, right? Now, when you look at this, what do you think of in traffic flow? Fundamental diagram, right? And actually, that's the topic of a future paper. Yeah, but yeah. And that's the analogy we're playing with right now. That, yeah, traffic is a fluid, and it behaves just in this way, all right? So, for example, this would be the MFD of Zurich, okay? And now, if I use the ideas from these power laws relationship, right, the beta, it turns out Zurich have a 1 over beta of 1.5. Fluids, they're all the same, right? They all obey the same rule, the same law, which is characterized by the 1 over beta being 3 point something. So for urban networks, it looks like it's going to be in the order of 2 or maybe a little less. That's the conjecture. So, yeah, that's the conjecture. Maybe this critical exponent beta for urban networks will be independent of the city. Now, this result, you're the first crowd to know this result. Hopefully, yeah, it'll see the light of day. But yeah, I think it's a very, very interesting idea. Now, if you extrapolate from this, you could think that instead of using computer simulation to model urban networks, you could use chemical reactions. A different way of doing simulation, right? Yeah, so yeah, that's a very far-fetched idea, but who knows? Maybe, you know, they're so complex that computer time is, you know, could take days. And maybe chemical reactions are, in fact, a shortcut of doing simulation. All right.
Can I?
Yes, please.
Question mark over there. Did you verify from city to city the beta, small beta 1.5?
Yeah. Question mark because yeah, we've starting to collect the data and look at. So I'm not sure. Now I've looked at a fair number, and yeah, they're all around 1.5 to 2 kind of range. But again, I mean, when you're dealing with urban network data, such as this one, nothing is normally distributed. So the statistics that you need to use are not given by any central limit theorem that we know of. So yeah, testing hypotheses, right, are the same betas across cities. That's going to take time because we need to identify the right kind of distributions. But if I get to the end, which I might not, the distribution of flow turns out to be this airy process that I talked to you about. So I think that would be the direction. All right, and then self-organized criticality, which wasn't the title, right? Okay. So water, if you want to boil it, you need to crank up the temperature, right? So we say that you have to, you need an external kind of control variable. There are systems in nature, mostly in civil engineering, by the way, that you don't need this controller. They tend naturally to the critical state. And that's bad news, right? Because the critical state is chaotic, right? There's power law behavior, nothing is normally distributed. It's unpredictable. I mean, it sounds bad, I know, but there's a way out. There's a way out. All right? So all civil infrastructure networks have this problem, like the electric grid, right? There are power laws in the sense that the number of links from a given hub is power law distributed, right? So it's going to tend to be critical, right? So blackouts are explained in this way. Yeah, supply chains. I mean, let's not talk about the supply chain problem for a day. We have wars, pandemics. I didn't put them here, but unfortunately, yeah, they're so timely subjects. They all subject to the same kind of problem, this self-organized criticality. Earthquakes, I mean, you name it, it's all over the place. And of course, traffic flow. All right, so to understand self-organized criticality, the authors that came up with this theory came up with a very simple example to explain it. It's called the sand pile model, all right? So you start with an empty table like that, and you start throwing sand from kind of randomly, right? Throwing sand, and then a little pile will pile up, I guess, until the slope here, it's critical, which means that if you add one more sand pile, you're going to cause an avalanche, okay? And these avalanches are bad news, right? And needless to say, they follow a power law distribution with an exponent of around 1.19, okay? So very unpredictable again. And this is amazing. I mean, this is pervasive in all those systems that I showed. They kind of follow the same kind of concept. And the idea is, how can we prevent these avalanches, right? That would be the best way to control. All right, and the power law exponent is a measure of resilience. So the higher the exponent, the more resilient is your network. Right, again, a small exponent means that there's no mean or variance. So it's very unpredictable, very not resilient, okay? So in the case of traffic, avalanches would be spillback, congestion spillback, right? Spilling back from one intersection to the next and then creeping up over the whole network, right? So the size of the avalanche in that case would be kind of the number of links that are congested due to something happening in a particular intersection, okay? And another big takeaway is that people like to think of what caused a given avalanche, a given earthquake, a given any type of the problems we saw. And the answer is that there's no special reason why this earthquake happened. There's no special reason why this big, gridlock happened in my network. It's just another grain of sand falling. The problem is that there's a history that accumulates in the system, okay, that stays there forever, right? And that's what makes it so unpredictable, because one cannot keep track of all the particles in the system. All right, so this problem was pointed out by Nagel and Paksukis in 1995, actually. And yeah, it was a physics journal, but mind-bogglingly, it kind of didn't have any impact. I mean, I didn't know about this concept until maybe a year ago. But he said clearly, I mean, traffic seems to be SOC, and therefore, the way to control it is to be suboptimal, right? You don't want to push the system to the critical state. You want to push it, way ahead of the critical state, so keep it in free flow, right? Don't push it to the maximum flow, right? And that's a bad thing of traffic, is that the optimal, we think, is to maximize the flow. That's what I've been told to do up until recently, to minimize the delay, right? If you want to minimize the delay, you have to maximize the throughput. But this is saying, no, wait a minute. If you do that, at some point, you're going to have an avalanche, and that's going to be catastrophic. Okay? So this observation is in contrast with what we do today.
So in that paper,
Yeah.
what's the foundation for them to make that statement? It's not power law.
In that paper, they saw the connection with the random walk. Yeah, and they do talk about power loss. Yeah, but yeah, I forget the specific reasoning behind it. But they were the first to conjecture it. Yeah. Yeah, and actually I was so surprised that it didn't have any impact that I contacted the authors and some other physicists that I know, and they were in the same boat. I mean, yeah, we don't understand, but nothing happened to this in all these years. So hopefully now it will be a comeback if some of you are interested. Okay. So yeah, let me just show you pictures now of traffic. This is the traffic flow surface again with different colors in 3D. I was having too much fun, and I just put something that looked like water there to make the connection with nature landscapes, which is a fractal, right? And those are all the ingredients we need to prove SOC. So you need power law behavior, you need to show that it's a fractal, and that the critical point is like the natural optimal state of the system, which is true for traffic, right? Because when you're driving the car and the light turns green, you try to go, right? So that's why, actually, urban networks are SOC. It's because we like to drive the fastest we can, right? So we're automatically, like naturally, trying to get to the critical point because that's the optimal for us. So yeah, traffic is naturally driven to the critical state in that way. All right. Yeah, this is actually the traffic flow surface. Let's keep the main concept for the paper, but in what we call the variational formulation of traffic, we look at the traffic flow surface right here, right? So this would be the vehicle number. So this is the first trajectory. This is space and time. So this is the first trajectory of the first vehicle. That's the second one, right? And it grows like that. So each layer is a vehicle, actually, okay? And yeah, this surface is the fractal one. Well, everything would be a fractal after, but this is kind of the starting point. All right, so in this variational theory, the way to, let's say, solve the kinematic wave model, right, which is the traffic flow model, which is equivalent to the CA model and everything, but it tells you, so at a given point, what you have to do is solve a minimum path problem from here, whatever point you want the answer to the boundary. All right, so sometimes it's going to be cheaper to come this way, other maybe come this way, right? So in essence, it's going to be a minimum path problem over a random network, or a network with random costs. And the network is a continuous network. I don't know if you can call it a network either, right? But yeah, you're trying to solve minimum path problems from every point to the boundary. All right, and yeah, and that's connected again to this Airy distribution thingy. All right, but what we showed in the paper is that this problem of minimizing, it comes back to a problem of finding the minimum of a Brownian motion or a random walk. All right, so here we have again the random walk on top. And this is just one illustration. Now we have space that way in the same way we started the talk, and time goes down. All right, so yeah, this is CA 184. So what we're seeing here, again, it's these jam clusters, right? The congestion waves, stop and go waves going against traffic, but also we see the voids. So these are so if you take a picture, you would see pavement, so no vehicles there. And then the gray parts would be capacity, the capacity state, right? So here you have all the vehicles traveling fast like that until they hit these jams. All right, so again, if you want the traffic state at this point, you should solve a minimum path problem, right? Which gets to here, and then the random walk is kind of the terminal cost of that problem, all right? But at the end, what you want to find is the minimum of this random walk. All right, so to see what is the length of a jam, right? So, or the duration, if you will, right? So you take a point where you have a clear jam and that stops, and that by this theory that I just told you, if it's going to be the back of the queue, right? Because right here there's free flow, and right here there's congestion. So it means that's the back of the queue. The cost from going to point D should be the same as going to point U. That is what variational theory would tell you, okay? So that comes down to identifying in the random walk 2 points that have the same height. And that is what we define as the return period, right? So by extension, so the return period is this whole thing, right? So the duration of the jam is half of that, just by looking at the figure. And that's kind of the main result, is that the jam duration is half of the return period, which is known to be a power law of exponent 1/2. All right? And yeah, so this is the exponent 1/2. You see here, what I show here is the distribution of these clusters, right? So the amount of cells, if you will, that are red or green, right? So each different color is a different cluster, like that. And that's the power law. All right. Yeah, that's another kind of version of the same figure. Maybe it's clear. So there's a one-to-one mapping, okay, with the traffic state to the area under the random walk. All right, so that's kind of the connection we established in this paper. All right. All right, so the main implication for the way we do things today, I would say, is encapsulated in this equation. I tried to show no equations, but I guess I had to, right? So what is the AJ? Is the area of jams. So it's the total area where you see a color. It's the number of cells that are colored here, right? That's congestion, okay? And it turns out that that area, that means proportional to. So it scales as the length of the system, so that's just the length of the road, to the exponent 3/2, so 1.5. Right, and that's because it's 2 minus the power law exponent that we found a minute ago. Right? So in traditional, let's say, science, we would expect that it would scale like the square, right? Because it's an area after all. So if you double the size of a square, the area of the square is going to be, the size square. But because we have fractals, the exponent is not 2. It's going to be 2 minus whatever the exponent of the other is. All right. Yeah, that's pretty much it. This is just pictures showing with the same model, but with stochastic, the probability of stopping. It turns out that the slope of the power law is closer to 1 now. Right, so before it was the deterministic traffic flow model. But if you add this probability of stopping, then the exponent tends to be closer to 1, which is better than 0.5, because it's more resilient, but still in the area where you don't have variance or mean. All right? Just another picture, hopefully reminding you of a landscape. Very good. And yeah, this is the last one. It's very recent developments. So it turns out that traffic is what physicists call, it's in the KPZ universality class, which is a very active area that affects all surface growth processes, from bacteria colonies to forest fires to you name it kind of thing. And now traffic. Now, they showed it only for this CA model. So that's the stochastic model that I showed you, right? That's the Nagel and Schreckenberg model. I'm sure it's going to be true for any model because universality, right? The details don't matter for universality. All right. And this is the one that's really recent. And so this class has a fixed point. So what this means is that all these systems will converge, in large system size and large time to the Airy sheet or the directed landscape process, which is kind of this thing. So in fact, we know everything statistically about what's going on here, right? So actually prediction looks like could be possible. If you're looking at the long-term flow of a given portion of your network, et cetera. All right, a special case of this process is the Tracy-Widom distribution, which it's also very new, but sometimes some of you might know it because it's all over the place now. It's kind of the bell curve of the 21st century, Tracy-Widom distribution. It's kind of a limited distribution that appears everywhere now, including traffic flow. So with that, my friends, thank you very much.
Try to understand. So, why CA? Why? We have a lot of CA different time, right? So the one particular CA is 184, right?
Yeah. So the CA84 is equivalent to the kinematic wave model,
Right.
with isosceles fundamental diagram. Yeah.
So that's how the service was generated from that particular.
Yeah, the pictures, yeah. I did all with that, yeah. The traffic flow surface. Yep.
Are there different groups that would represent better different fundamental diagrams?
There might be, but what is shown is that you don't need that. It's actually, it's isosceles will give you the same results as if you use any other triangle with the slopes. Yeah, so technically we say that the conservation law is invariant to that transformation. So it leaves everything the same. So if you're interested in the delay, no matter what triangle you use, you're going to get the same number at the end. Now, there's variables that are not invariant, but the ones that we care about, they are. So delay and flow, those are invariant. Yeah, that's a very unusual concept in our discipline. We published it way in 2016, I think. And I think I'm still the only one using it. And Daganzo also. Yeah, and actually something I forgot to mention is that when I say traffic flow, I really mean bicycle flow also, pedestrian flow, they're all the same. There's a fundamental diagram very similar. And then, so all these results kind of extend to all modes of transportation. even airplanes on the taxiway. Maybe not in the air, but yeah, and also I mentioned the Ganzo, so he used this transformation, the isosceles thing, for his work in logistics. So logistics too is kind of the dual of traffic flow. It's like you're solving the inverse problem in a way. So it's kind of everything is connected in some unexpected ways, which I found fascinating. Yeah, thank you for your questions. Appreciate it. Yeah.
Can you explain the area distribution again one time when you were showing the
Yeah.
random walk?
Yeah. Yeah, so you have a random walk, and then you identify a return period, right? So you come back to the same. So the area right here obeys the area distribution. So technically this, so from here to here, this is not a random walk, is a conditional random walk, right? And the conditions are that it has to be positive, and you have to come back to the same value, okay? Yeah, so in that sense, that's the area distribution. All right, and then since we're looking at this, also, if you take these areas independently as random variables, right? So you make a list. This is, okay, 10, area 10, 1, 1, 2, 2, et cetera, for all these areas, all right? And guess what distribution that is? Power law. Are we still being recorded?
Yeah.
Oh, okay. Because I wanted to say.
I can. 3 minutes.
Yeah.
Yeah, thanks for exposing into a lot of new concepts. So can you elaborate on everything, what is the relationship between everything that you presented and the sort of conclusion we started with, that we are going to be worse off with more data?
Trying to connect everything, wow, that's a tough question. There's an underlying backbone to all of this. And I didn't want to go into too many details, but it's percolation. Percolation is a very fun process. And these are the slides that I skipped right here. Right? So in percolation, so we have this, think of time space again, right? And you have these clusters. So these clusters, the different colors means that if you put an ant right here, it'll be able to walk, to reach by stepping only on the cells that are 1, right? So you have all these clusters, right? Now, at the critical point, these clusters percolate. Now, percolation means that, like in this case, the yellow one goes from one end to the other. So percolates means just flow through. So this one just flows through, you could make water flow, right? That's percolation. In traffic, it looks like this. So when it's fully congested, right, the congestion will propagate all the way through your segment. So they're percolating in a way. In free flow, what percolates is the voids. So the absence of vehicles, right? They kind of percolate. But in the critical state, you cannot tell. You cannot tell if you're going to end up with, right stripes or left-going stripes, this kind of thing. So right at the critical density, right, what happens is that nothing percolates, or it's very difficult to see if you're going to have a percolation of free flow or congestion. And these are 2 examples, right? Here's the free flow that percolates. Now the critical density is 0.5, so here we're just under, so it's 0.46, right? And here's a little over 0.5. And here's congestion percolates. So that's kind of the phase transition that's going on. It's right at the vicinity of the critical density where you're not able to tell if it's going to percolate one way or the other. Okay? It's kind of a discontinuity in the initial density at that point. Yeah, and this percolation phenomena is why SOC is so prevalent, right? So in earthquakes, this percolation of the tectonic plates, so the energy that accumulates, right? When you have a big avalanche, it's because you have percolation. That network of the energy stored kind of propagates through the whole thing. And so that's kind of what glues together, I think, all these concepts. Now you mentioned also the data.
Yeah, so is there a relationship between, so I understand the concept of this critical density and it happens in nature. Why is it that with more data will be worse off? If you are going to be better off if we have smaller data sets and more data will be worse off?
Right, because so when you're at the critical density, the data that you would get, it's going to be chaotic. It's not going to follow any pattern that you will be able to figure out.
So the size of the cloud basically is critical increases. But when you're working with a smaller data, you just have the data from one scenario. It's overfitted to that scenario. So the true answer is that there is no pattern. But when you have a smaller data set, you think you have a pattern.
Right.
But that pattern is only fitted for that specific scenario, right?
Right.
So isn't it the case that with a bigger data set, we actually come to the right conclusion that there is no pattern?
Yeah, I mean, you might be right, in the limit of infinity. Yeah, and this goes back to the idea of the law of large numbers not converging, okay? So when you have a power law with index around 1 or so, people have shown that you would need trillions of samples in order to get some idea of convergence. So yeah, the answer is that the amount of data you would need to do that, there's not enough time in the universe, so to speak, to observe it. Yeah, we're kind of tiny observers in this giant space that opens up, right? All we can see is kind of our immediate neighborhood, but there's this overwhelming, space of, yeah. All right, thank you for your patience, guys. I know we went overboard.